kicking off homework 4, part A, with question 1. We are asked to use force balance and definition of Newtonian viscosity. We will derive an expression for laminar viscosity profile in a horizontal cylindrical tube. As we normally do, we can draw a picture. Scoot over. Of a horizontal cylindrical tube. This tube is going to have two radiuses that we consider. One is little r, that will be in terms of the direction, and this r here, which just goes to the edge, but I drew it kind of small, so here you see is r, and that's once you reach the edge of the actual tube. So for this, it's going to be similar to our last problem, how we were able to relate our stress to force over area, and then that is also equal to our mu over sigma. And then from here, we know that our sigma is equal to the differential volume over a radius. So we will plug this into here, and then we will actually multiply both sides by area to cancel on the one. That'll look like F equals mu sigma area. So what is our area? Our area is going to be two pi r times L, because we are considering this over this. So again, plugging this into this and this into this, that will be mu dv 2 pi rl, all divided by our dr. So from here, we also need to take into account the force that is from our pressures. Lost my train of thought there. So our pressures, we're going to have a P1 here and then a P2 here. These pressures, it'll be a difference going in and out, and that'll be also times an area, which is pi r squared. And this equation that I've written here, we can move down to being a little bit better. As equal to 0 because the system that we are working in. So from here, we're going to want to isolate our differential volume and move our dr and everything else to the other side. To do that, we can start by moving over our change in pressure, and that's actually going to make it positive because these will switch to like this, which we know as that. So pi r squared. From here, we can actually cancel, I'll do it in red so it's a little bit easier to see, our pi's, and this r will cancel, and making this exponent go away. And then, as I said, we'll rearrange some of our variables to get our dv alone in a place that we can integrate both sides. So that will end up looking like dv is equal to change in pi r dr over our 2 mu L. And as I said, we will integrate both sides. That integration is pretty easy. We just get V, and then we get to bring out all of our constants, which is actually just going to, if we take out these guys, we're just left with r dr, which if we integrate equals r squared over 2. So I'm going to go ahead and write that here. And then in this instance, we will actually add our constant that we don't know yet. So to find this, what is c, we will consider when r is equal to r, we know that our velocity is equal to 0. So when those are equal, we know that there is no velocity, which means we can substitute big R for little r in this equation and our 0 for v here. So again, doing that is going to look like 0 equals change in p r squared 4 mu L plus c. So solving for c, you get a negative change in pressure r squared over 4 mu L. Now if we substitute what we found here back in to here, that is the last step of this problem before we move on to the next part. We get change in pressure times our directional r squared over 4 mu L minus a change in pressure with our big R squared over 4 mu L. And like I said, that is our last step. We can square that in. All right, moving on to question 2 of homework 4, part A. We will be deriving from the first question an expression for flow rate as a function of pressure drop, fluid viscosity, and pipe length and diameter. So I did go ahead and pull the equation from the prior problem down. And then I'm going to go ahead and condense this a little bit just so it's more concise and a little bit easier to work with. That will just look like factoring out our R's. And then we want to relate this to flow rate. So flow rate is defined as being equal to velocity times area, or velocity integrated with the differential area. So breaking down our differential area, that's going to look like if you cut a section of our pipe, here's our center, and then if you were to make rings in this, we're going to identify this as dr and the area as 2 pi r. So plugging this, what we just found, into here, we now get Q is equal to V times 2 pi r with respect to a differential radius. Plugging in our V here, our expression into here, we can see that Q is equal to the integration of a change in pressure over 4 mu L times r squared minus r squared times 2 pi r dr. Pulling out some constants, I'll underline what we're going to pull out in red here, and then we're actually going to be able to factor that in or distribute. So this is going to look like Q being equal to change in P, 2 pi r, no, sorry, not R, over 4 mu L. So that gets rid of this and this and this. We can also simplify this down to 2. And then we're left to integrate R cubed minus R squared times R with respect to the directional R that we've defined. So that integration is going to give us a change in P times pi over 2 mu L so R to the 4th over 4 minus R squared over 2. And that again is from 0, oh, I didn't write it the first time, from 0 to R. So until you reach this R. So plugging this into the little r's, we get our equation of 2 pi, or I'm sorry, change in pressure over pi, change in pressure times pi over 2 mu L times our R 4 over 4 minus, this will be 4, well, this will be 2, and then that'll be 2 times 2, which is equal to 4 over 2. So if we subtract these two, you're going to get R to the 4th over 4 times the negative. And then we can pull that and simplify this expression to equaling the volumetric flow rate as it relates to its fluid viscosity and pressure drop, pipe length, and diameter is going to be Q equals change in pi, change in pressure times pi times R to the 4th negative. And then our 4 times our 2 gives us 8 mu L. That is our volumetric flow rate for question 2. All right, homework for part A, question 3, from 2, derive expression relating friction heating to flow rate, fluid viscosity, density, pipe length, and diameter. So we can move down what we wrote in our last problem as Q is equal to a negative pressure change times R to the 4th times pi, all over 8 mu L. All right, so now that that is there, actually before I forget, because this one's kind of a long one, I'm going to go ahead and write Bernoulli's equation. I think that is how you spell it, but that is a change in pressure over density plus gravity times change in height plus your difference in velocities squared divided by 2 is equal to your negative potential energy. Sorry, not potential. Your negative internal energy plus move this down so it's all in one line, plus your differential heat with respect to your mass, plus your differential work from non-flow over your mass. Okay, glad I remembered that one. So because we want this in terms of diameter, I'm going to go ahead and take this and substitute out our radius. We know that our radius is just our diameter divided by 2. So if we go through and do it to the power of the fourth, to the fourth power, I guess, 2 to the fourth is equal to 16. So we're going to substitute that into here. All right, that is going to be Q equal to a negative change in pressure times d to the fourth times pi all over 8 times 16, which equals 128. Keep switching over to the eraser. Times mu times length. Make sure that negative sign can be seen. And then from here, I'm going to backtrack and look at our Bernoulli's equation. I hope that green is okay through the camera. We know that there is actually no work added to the system from non-flow. So we're going to be able to cancel that. We know that there's no change in height from our picture that we drew, I guess in question 1 here. There's no change in height. There's just the distance L. So we also know that for our velocities, we will choose points where velocity is equal to 0 to make this simpler. So we can get rid of that as well. Therefore, what is left in this equation, or 1 on each side, is going to be equal to a change in pressure over density is equal to a negative change in internal energy plus our dq dm. And this, we know, is actually equal to a negative friction due to heating. So that is our internal plus our external heat, and that can be identified as a friction heating. Yeah. Oh. Friction heating is here. So what we're going to want to do is figure out a way to incorporate this, and that will be done using this equation. So if we look at Q being equal to negative change in pressure diameter to the fourth times pi over 128 mu L, we will actually just move everything around to get here. And that's going to look like change in pressure being equal to a negative 128 Q times our mu times our L. That gets rid of this and that. And then dividing our whole thing by a diameter to the fourth times pi. From here, the last step is to divide both sides by this density to make this being able to plug in to our equation here. So when we do that, we actually end up getting that our negative friction from heating is equal to our negative 128 Q mu L over d to the fourth times pi times density. And then that actually ends up being able to cancel both of our negatives. So I'll erase those and box this in as our final answer for homework 4, part A, question 3.